Good morning, everyone. I'm Adyasha Mohanty, and today I'll be presenting a particle filtering framework for integrity risk of GNSS-Camera sensor fusion, done jointly with Shubh Gupta under Professor Grace Gao at Stanford University. In deep urban canyons, GNSS signals suffer from signal blockages, non-line of sight errors, and multipath effects which lead to errors in state estimation. Thereby, it's important to assess the integrity of the navigation system, formally defined as the measure of trust in the correctness of the positioning solution. Typically, integrity is provided with RAIM that performs consistency check of redundancy of range measurements and alerts the user if the positioning error exceeds a certain tolerance level or the alert limit. Although classic RAIM techniques work quite well for GNSS only, there is a need to augment GNSS with additional sensors and perform integrity monitoring for sensor fusion. This is because standalone GNSS provides coarse positioning estimates due to errors inherent in the GNSS signals because of urban canyon. By incorporating redundancy in measurements through additional sensors, we can overcome the challenges associated with GNSS-only navigation. In our work, we choose camera as the additional sensor since it is inexpensive and does not suffer from drift errors like IMU. In deep urban environment, GNSS and vision act as complementary sensors. Vision offers strong sensing due to abundance of features present in the environment, whereas GNSS signals suffer from multipath and signal blockages. Augmenting GNSS with vision, however, introduces errors due to incorrect association of features and images. For example, the image on the right shows that similar features such as edges can be found in multiple regions of the same image, creating ambiguity during feature association. These errors are further amplified due to variations in lighting, occlusions, and other environmental factors, all of which can degrade the positioning solution. Thus, we need to provide integrity for GNSS vision sensor fusion. To account for vision faults along with GNSS faults, we also want to account and mitigate the errors that arise during sensor fusion from contamination of measurements from GNSS and vision so as to maximize their complementary characteristics. Recent methods for providing integrity for sensor fusion include using variants of Kalman filter, such as EKF or information filter, alongside robust estimators. Factor graph optimization is also another recently proposed technique. These approaches function quite well. However, they make one limiting assumption of addressing state estimation and integrity monitoring separately. The positioning estimate is first formed using multiple sensors, and then the solution's integrity is assessed. Adopting this approach does not capture the uncertainty present in state estimation, which might bias integrity monitoring and subsequently lead to faulty positioning estimates. Recently, a framework for joint state estimation and integrity monitoring was proposed in particle RAIM. Instead of assuming the correctness of a single state estimate, particle RAIM forms a likelihood over the state to keep track of multiple fault-aware position hypotheses, otherwise represented as particles. The reliability of the GNSS ranging measurements is first assessed with traditional RAIM, and then the particle weights are updated to form a distribution over the state. The integrity risk is then calculated from this distribution, leveraging concepts from statistical learning theory. Although the proposed framework is effective at multiple fault exclusion, it produces coarse positioning estimates due to its reliance on GNSS measurements only. This requires us to employ conservative measures, such as large alert limits, to adequately provide integrity for the navigation system. Thus, our objective today is to jointly address state estimation and integrity monitoring for GNSS and camera sensor fusion. We also want to quantify the uncertainty in camera measurements by deriving a probability distribution over the state. We want to account for vision faults due to data association errors while inferring this distribution. And lastly, provide a framework to combine the distributions inferred from GNSS and camera measurements, ensuring minimal cross-contamination. We propose the following contribution. We jointly estimate the position and provide integrity for GNSS-Camera fuse system using a particle filtering approach. We derive a probability distribution over position hypotheses from images. We develop a metric to fuse probability distributions learned from GNSS and camera measurements. And finally, we experimentally validate our proposed framework on real-world urban environment datasets with existing errors in GNSS and camera measurements as well as add false. Our overall framework presented here is based on a particle filtering approach, as it allows us to keep track of multiple hypotheses over the position and model non-Gaussian and multimodal measurement likelihood. The highlighted modules represent our contribution, and the GNSS and the integrity responding modules are directly adopted from particle array. In the perturbation block, we generate a set of motion samples using noise odometry, each of which further perturbs the initial particle distribution in the propagation step. The GNSS module then takes cross range measurements from multiple satellites and outputs a measurement likelihood over positions using a fault-tolerant weighting scheme. Since GNSS and camera measurements are acquired at different sampling frequencies, we forward propagate the states underlying the camera measurements with IMU motion data to synchronize them. The camera measurements are also fed to the camera module that outputs a likelihood over the position hypothesis. During probabilistic sensor fusion, we use a divergence metric to output a joint likelihood over positions. The particle weights are then updated in the resampling step to generate the current particle distribution that is taken in by the integrity responding module that produces an integrity response derived from this distribution. First, I'll talk about the different modules of the proposed framework. Then I'll discuss the results obtained from experimental validation, and finally I'll conclude and summarize my talk. The GNSS module is directly adopted from particle array. It basically imports a distribution over the position from GNSS ranging measurements. The likelihood from a single measurement is represented with a Gaussian distribution that is derived using a dilution of precision period state. The likelihood of all ranging measurement is modeled as a Gaussian mixture model to represent the multimodality of measurements. The weight associated with each Gaussian component is inferred with a single-step expectation maximization approach. In the expectation step, each particle casts a vote for each measurement based on the square normal voting on the normalized residual from RAIM. Because of this step, we are able to achieve a deeper coupling of state estimation and integrity monitoring, wherein the RAIM-based voting scheme directly captures the uncertainty in the state through the confidence parameter associated with each GNSS ranging measurement. In the maximization step, the votes are normalized across all measurements and particles and pooled using Bayesian map estimation to finally form the GMM. Moving on, we now need to infer a similar distribution of the position from images. We use a data-driven map matching algorithm that matches the test image directly to an image present in the database. Our algorithm is robust with respect to typically occurring faults in images, such as occlusions, blurring, varying lighting conditions, among others. Additionally, the algorithm is scalable in terms of the number of images required to construct the database and perform image matching. Our method is implemented in OpenCV and comprises of 3 steps. The first step is creating a database with images extracted from the mapped area. In the second step, we perform image registration to match the received test image with respect to all the images found in the database. Finally, in the last step, after getting the best matched image, we can extract its coordinates and then generate a distribution over the position hypothesis. Now I'll describe the individual steps in more details. In the first step, we use GPS coordinates to select a mapped area. Then, we select certain images in this region using Google Street View imagery and extract their associated coordinates to construct the image database. Features are extracted from these images and then stored in a key point descriptor format. Simultaneously, we extract features and descriptors from the test image. The descriptors are then clustered with K-means algorithm to form a vocabulary tree. Each node in the tree represents an inverted file with references to the images from the database, which contain an instance of that node. The training database is then scored hierarchically based on term frequency, inverse document frequency scoring that essentially represents how relevant each image in the database is to the given test image. Based on these similarity scores, we can find the matched image and compute the distance from the state underlying this image to all the other particles. Then a softmax function takes these values and converts them into a probability distribution over the position hypothesis. Now that we have formed measurement likelihoods from GNSS and camera, how do we intelligently fuse them to form a joint likelihood over the position hypothesis? In the previous step, we generated likelihood of a single camera image, which represents a non-Gaussian probability distribution. In order to identify and isolate faulty camera measurements, we need a way to assess the consistency of each camera measurement likelihood with regards to the GNSS measurement likelihood, one that we know is correct since the distribution is inferred by weighing the measurements to the RAIM routing scheme. Thus, we use KL divergence from the broader class of F divergences to assess the consistency by computing the divergence between each camera measurement and the GNSS measurement likelihood. Minimizing the divergence ensures that both likelihoods are consistent with each other, producing a tight overall distribution over the position hypothesis. First, we represent the likelihood of all camera measurements with a mixture of exposed model, where each component represents the likelihood inferred from a single test image in the camera model. Each measurement likelihood is then assigned an unknown weight to represent its contribution in the mixture. Next, we set up the KL divergence between each camera measurement likelihood and the GNSS likelihood to infer the component weight. Again, the idea is that the weights represent the optimal way of including additional camera measurements that do not contaminate the existing GNSS measurement likelihood. Then we minimize each metric with respect to the weight assigned to it to obtain a closed form expression in terms of the overall GNSS measurement likelihood and the camera measurement likelihood. Finally, to infer the joint likelihood, we multiply the mixture distribution with the GNSS likelihood, assuming they are mutually independent. In the last module, we compute the integrity risk associated with the distribution from the particle filter as proposed in particle RAIM. First, we create multiple posterior distributions by using motion samples, for instance, with odometry data. From these perturbed distributions, we compute the PHMI, formally defined as the probability that the true position exceeds a certain reference position within certain bounds. From these perturbed distributions, we can then compute the expected risk along with the uncertainty that is not captured in these distributions to generate the integrity risk bound. Using packed Bayesian bound-free statistical working theory, this integrity risk bound is formally shown to provide an upper bound to the reference risk. The reference risk represents the true risk associated with the reference position computed using ground truth. Thus, our goal in this module is to overbound the reference risk with the derived integrity risk bound in order to successfully capture the false in state estimation. Now I'll be discussing the results from the experimental validation of our framework on real-world urban dataset. Specifically, we use an urban driving dataset from Frankfurt that contains small line-of-sight errors in GNSS measurements and vision faults. We use ground truth to range measurements, camera measurements, and IMU motion data. We also create emulated datasets by inducing faults in GNSS and vision measurements with various control parameters. For GNSS, we remove the existing non-line-of-sight errors but add Gaussian bias noise to randomly selected satellites at random time instances. For camera measurements, we add Gaussian blurring and occlusions of varying sizes to randomly selected images. The table here shows the experimental parameters used for all our test cases. We use about 120 particles to estimate the 3D position of the car. We vary the number of faults in GNSS ranging measurements from 2 to 9 out of 12 available ranging measurements at any time step. The added bias value is also varied between 20 to 200 meters. To validate our framework, we use 3 metrics. The state estimation performance is evaluated based on the root mean square error between the estimated position and the ground truth. The risk bounding performance is evaluated based on the failure ratio, which basically counts the number of times the derived risk bound from our probability distribution fails to upper bound the reference risk. From the incidence of these failure events, we can then compute the mean error in position estimation during these failure events, known as failure error, and also the average gap between the derived risk bound and the reference risk, known as the bound gap. For validating the integrity risk, we specify a performance requirement that the position should lie within the alert limit with at least 90% probability. Furthermore, we choose 2 different alert limits of 8 and 16 meters for this requirement. A fault occurs if our position exceeds the alert limit, and based on the incidence of fault events, along with the specified performance requirement, we can then derive the probability of false alarm, and the probability of misidentification metrics. For the first validation case, we test our framework with non-line of sight errors in GNSS measurements and added vision faults. Using particle RAIM as a baseline, we observe that our algorithm produces lower positioning error for all test cases with an overall RMSE of less than 11 meters. For the second validation case, we test our framework with added faults in both GNSS and camera measurements. Similar to the previous case, our algorithm here also tracks the position better than particle RAIM. Additionally, our algorithm reports lower incidences of regions where the mean error is larger than 5 meters, as shown in red, compared to particle RAIM. Quantitatively, we study the trends in the RMSE for different added bias values and number of faults in GNSS ranging measurements. For fixed number of faults, the error in state estimation generally increases with added bias value. However, at a fixed bias value, it becomes relatively easy to detect and exclude higher number of faults. Overall, our algorithm produces lower RMSE than particle RAIM for all test cases, demonstrating that the KL divergence metric is effective at mitigating vision faults and producing refined positioning estimates with GNSS vision fusion than with just GNSS. We now discuss the results for integrity risk in the next few slides. From these figures, we see that the derived risk bound in black overbounds the reference risk shown in blue for all test cases with a tight bound gap. Furthermore, these results are shown for an alert limit as small as 8 meters. The few regions where we fail to bound the risk are caused due to sudden jumps in the reference risk that are undetected by motion samples. A key thing to note here is that the incidences of these failure events is quite low across all the test cases. Quantitative results for the same alert limit of 8 meters here show that the overall probability of false alarm is less than 0.11. Overall probability of misidentification is less than 0.07. Additionally, the derived risk bound has a low failure ratio of less than 0.11 and produces a tight bound gap of 0.4 for all the cases. Here we show similar results for integrity risk, but with a larger alert limit of 60 meters. As expected, the integrity risk in these curves is much smaller compared to that obtained with an alert limit of 8 meters. This is because almost all the particles from the Kotak distribution now lie within the large specified alert limit. We also see that the risk bound for this case still overbounds the reference risk tightly for all test cases. Quantitative results for the same alert limit show that the overall probability of false alarm is 0 and the overall PMI is 0 for all test cases except 1. Additionally, the derived risk bound has a low failure ratio of less than 0.07. We also observe that the bound gap produced in all these cases, or with an alert limit of 60 meters, is about 0.1, which is much lower compared to the bound gap obtained with an 8-meter alert limit. So to conclude our work today, we jointly performed state estimation and computed integrity risk for GNSS-Camera fuse system with a particle filtering framework. We quantified the uncertainty from camera images by deriving a measurement likelihood using a data-driven approach. We also designed a KL divergence metric to probabilistically fuse measurements from GNSS-Camera, and we demonstrated the divergence metric's efficacy at ensuring that faults in camera measurements do not contaminate measurement likelihood learned in GNSS measurements. Lastly, we experimentally validated our framework on real-world data with augmented GNSS and vision faults. I would like to acknowledge Tara Mina and other members of the NAV Lab at Stanford University for providing me constant support, feedback, and encouragement throughout this whole process.